Hey, hello there. Today I'm looking at question 329, longest increasing path in a matrix. So we have an integer matrix, 2D matrix, and we want to find the length of the longest increasing path inside this matrix. The path is a sequence of locations in the matrix that are connected by the four directional moves. So we can go up one row, go down one row, go to the left column or go to the right column from any given position inside the matrix. To form a increasing path, we want to make a move if the neighbor has a value that's strictly larger than us. So let's say that we're starting with this row 2, column 2 inside this 3 by 3 matrix. If we want to use this as a starting position to build a path, increasing path, we could either go up or go right. And no matter which choice we make, that neighbor is going to be the termination for the increasing path, because from either 9 or 8 we couldn't go anywhere else anymore. So if we start with 6, after we explore all the options from there, we know the longest increasing path starting from 6 is going to be 2. So if we just code this subroutine, code this kind of a strategy exploration as a subroutine, we could essentially just run this subroutine on all the locations inside this matrix, and it's guaranteed that we will get a global maximum, longest increasing path, if we actually do this. But just very quickly we realize that we don't have to run this subroutine on all the locations, because if we consider 6, we notice that there is a neighbor that's just one row below us that has a value of 1. So instead of starting from 6 to consider the increasing path starting from 6, we should consider the path starting from 1, because no matter which path, whatever the longest path we can have from starting from 6, we can always just put 1 towards the left as the actual starting point and connecting 1 to 6 to get a path, increasing path that's 1 longer. So there are only certain locations inside this matrix we really want to run a either DFS search or BFS search to find the longest path inside the matrix starting from there. What are those positions? Those are going to be the position where the cell value is going to be less than or equal to all its immediate neighbors, because only if that's the case, it can be the starting position for the longest increasing path. Otherwise, if you have a neighbor that's smaller than you can always starting from that neighbor. So if we try to sort of like visualize this, if we just using arrows to pointing to the next neighbor that have a value that's larger than the cell value, you're looking like this. You become more looking like a graph now. Every individual location inside this matrix is basically a cell, a node, and the directed edge inside this graph is the 4 directional neighbor movements, where we can actually have the neighbor to be larger than us. So that will be the direction for the edges. The only positions that only nodes that we want to start the exploration to find the length of the paths we can traverse starting from that node is going to be those nodes that have no arrow pointing to it. So we're gonna that's just the nodes that with 0 integers. Any node that has an integer that's larger than 0, we can just go to the node pointing to it to try to run the DFS or BFS search starting from those nodes instead. So let's visualize this. If we were to choose to do the BFS search, it will looking like this. It will be level by level. We can definitely do DFS search. So if we starting with maybe 3, we can go right, and from there we can go right. The node 9 will tell node 6, if you choose to go to me, you will have a increasing path of length 2. So node 6 will note it down. So if I go right, I will have a increasing path of length 2. You will also try to go up and then go right. So 9 will tell 8, we together will form an increasing path of length 2. 8 will go back to 6 and say, hey, if you choose to go to me, you will have a length of increasing path of length 3. So that node 6 will have 2 pieces of information and takes the maximum and go back to 3 and say, hey, if you directly go to me, we together can form a longest path, increasing path of length 4. That's going to be 3 that I know of together with you, so it will be 4. So we can do this, definitely do this in DFS search. It will be post-order updating for the maximum length. And that's not the time that node 3 would know its full potential, because you haven't tried this downward path yet. So the downward paths will go to 4 and 5, and 5 will go to 7 and go back. 5 will also go to 6. 6 will tell 5 it's going to be 4. 4, together with 5 will be 4. 5 will tell 4 it's going to be 5. Then this 4 will go to tell 3 it's going to be 6. So 3 will have 2 possible numbers, 4 and 6. 4 is directly go to right, 6 is going down. So you do this maximum, and we can solve this by doing DFS search. But today I actually want to do the BFS search, which is more, more directly visualizing the sort of like a topological order of all the cells inside this matrix. So we will start with those nodes with 0 in degrees, and just go this level by level. The only time that we put a node onto the next level is when the in degrees decrease to 0. So after we explore the location row 1 column 0 with a value 3, we will decrease the in degree for this node 6 in the fourth level by 1. But it's not the time we should put this 6 onto the queue yet, because we really don't want to start exploring the subsequent paths yet, because including 3 and 6, it's only a path of length 2, but we have other paths that can lead to 6 with potentially longer. So that's the whole idea about doing BFS search. It's going to be level by level. The next level are going to be the node with the in degrees decreased to 0. The decrease is basically based on the outgoing edges from the current levels nodes. So I've done this for a couple of times now, so just gonna try to code this thing up very quickly. Yeah, so let's do this. So the first part is going to be the graph processing, and the second part is going to be BFS search, BFS topological sort, and to find the to count the number of levels, and we also need to find the starting position. So that's going to be the three chunks of the code. The graph processing we're going to do is to basically getting the out edges and also the counting up of the in degrees. So the total number of nodes inside this matrix is going to be the number of rows multiplied by number of columns. So we grab those in the beginning. Let's do some housekeeping because it doesn't mention that the number of rows and number of columns inside the matrix. So the number of nodes is going to be the number of cells inside the matrix. It's going to be number of rows multiplied by number of columns. And we're just gonna try to populating the out edges and the in degrees. the outer edge is basically the adjacency list, the representation for the graph. So we're going to do for row in range of number of rows, for column in range of number of columns. We will try to look at the neighborhoods to determine can we actually draw arrow points to the neighbor. We'll just write a really simple helper function to do this, to avoid indentation too much. We consider all the 4 directional moves. That's one row above us, one row below us, the same row but one column towards left, or same row the column towards the right. If that we're still within the board, we yield that location. So here it will be if this next location has a value that's strictly larger than this value, this cell value we're looking at. That means we can go to the neighbor to form a path that's one longer. We would just record this out edge from the current location to there. So that's that. And also increment the in degree for the neighbor. So this is the graph processing part. We can obviously see that we look at all the possible positions, and for every position we look at the 4 directional neighbors. So it's going to be order of 4n, and the space is basically the out edge is going to be potentially 4n, the in degrees is going to be n. So if we drop the constant, they both going to be on in terms of the space, and the time here is order of n if we drop constant. So that's the graph processing. With this we can try to find the possible starting positions. We define this as a queue, and it's going to be the locations inside this matrix where the in degrees is 0. So after this nested loop, double loop, we will have the first level, the possible starting positions for the longest path inside this matrix. After that, we'll just do level by level traverse, and whenever we follow the out edge to the neighbor, we'll decrement the in degree for that node. Once that node's in degree decreases to 0, it means that all the paths that leads to this particular node has already been explored. So we already count the number of levels prior to that node. That means that this is the time. This is indeed the level that this node belongs to. So that's going to be the BFS search code. So we just count the number of levels. going to call this length, starting with 0. While we have Q, we would do is to initializing a placeholder for the nodes that we can potentially explore in the next level. Would there be duplicates? No, there is not going to be. There is no chance it would contain duplicate. For node in the queue, or we can just do a loop. And we don't need this. So node would be the popping out the one of the node from the queue. Oh, so for this we actually need a deck. Okay. So it's really a queue now. So for the node that we popped off the queue, we gotta follow the out edges and decrement the count in degree for the neighbor. If the in degree decreased to 0, that means we have explored all the nodes that's one level prior to that. This is the time that we can actually put this onto the queue. And after we've done this, or actually before this, we can increment the length. So in the end, we can return the length. So let's see if we have problems. So this is the edge case handle here. If the matrix is nonsense, we return 0. It's totally empty, then there's no path. That means the maximum length for the path is going to be 0. Otherwise, there has to be at least 1. So we can grab the number of rows, number of columns, and then calculating the total number of nodes. And then what are we going to do? Do I really need this n here? Anyway. I don't think so. So I can just remove this. I guess I calculated it because I want to say instead of doing this time space analysis with number of rows, number of columns, I can do that directly with this m. So we're gonna populate the out edges and also the in degrees. The out edges are gonna be the directions, the relationship between the cell value, the location in the matrix, to its neighbors that it can actually move over to form a increasing path. So that's basically trying all the positions inside this matrix, looking at the 4 directional neighbors, and then just compare the cell's value with the neighbor's value. If the neighbor has a strictly larger than value compared to the cell, that means we can go to there. So we record this onto this adjacency list of the out edges, and also increase the in degree count for the neighbor. So that's the graph processing part. It's 4 multiplied by n actually. So then we find the possible starting nodes to those increasing passes. This is also order of n here, you can see. And the queue, I guess the worst case for the queue is going to be order of n as well. That's the case when the matrix just have the same value all around. So the all the nodes are going to have in degree 0. So we ended up actually putting everything onto the queue. So that's the linear space with respect to the total number of nodes. After that, we pretty much identified the first level in the topological sort order. Then we're gonna iterate over popping all of those nodes out, all the first level nodes out, and for every such node, we try to follow the out edge and to decrease the count for the in degree for the neighbor nodes. Once the neighbor nodes in degree decrease to 0, that means we have already considered all the paths that leads to it. That means it's the right time to put this node onto the queue. So that's this statement here. So every layer, after every level, we increment the length for the count by 1, increase this count length by 1. So in the end, this length should be the maximum length. And the time complexity for this is going to be 4n as well. Because every node here, the out edge, the number of stuff on the out edge is going to be upper bounded by 4, and in the worst case, as we already say here, it's going to be n, so it's going to be 4n. Or you can say that we pretty much are just going to visit every node. Every node is going to be on the queue exactly once. So at any given time that we really processing that node, the time for that is going to be upper bounded by 4, so it's 4 multiplied by n. That's the time complexity for this. Let's see if the code works. It seems so. Yeah, so that's the BFS topological sort solution to this question. Yeah, so that's that. I also briefly touched that we can actually run DFS. Yeah. Anyway, I don't have time to do that today, and this week I'm just practicing topological sort, so that's why I was doing this solution instead. Overall, the time and space for this topological sort solution is a constant multiplier by the total number of cells in the matrix, so it's linear in both time and space. Yeah, so that's the question today.